尊敬的谢志伟主席，尊敬的我们澳大的前校长周校长，尊敬的姚启智教授，今天我们澳大十分有幸，请到了世界著名的计算机科学家、图灵奖的获得人姚启智教授，为我们做一次精彩的讲演。Dear UC Council 谢志伟 Dear former Rector Zhou and Professor Yao, we're very lucky today that we have invited the very famous computer scientist and the winner of Turing Prize, Professor Yao Qizhi, to give us a very interesting lecture. On behalf of University of Macau, let us give applause to welcome Professor Yao. 让我们掌声欢迎姚教授。Perhaps many of you already heard that tomorrow, or actually the day of tomorrow, Professor Yao will become one of us. This is because we were going to award him the honor doctorate degree. Professor Yao has accomplished significantly and outstanding on many aspects in computer science. And you already have introduction in hand, I'm not going to repeat it. Simply just look. He actually was a professor taught in Berkeley, Stanford, MIT, Princeton, and now the Tsinghua University. So I'm not going to waste time to go through all his resumes and accomplishments. 所以他已经取得了非常非常伟大的成就。只看看他在哪些大学任过教，是美国的 Berkeley 大学、美国的 Stanford 大学、Princeton 大学、MIT 和中国清华，光这几点就说明他的伟大成绩，所以我就不再浪费时间来重复这一点。But I'd like to talk about something special relevant to Macau. First of all, Professor Yao was the very first Asian, of course, the very first Chinese to win the Turing Prize. Many of us know that. 姚启智教授是第一位亚裔，当然也就是中国裔的教授来得到图灵奖。大家知道，图灵奖在计算机里边就等价于诺贝尔奖。But many of you perhaps did not know he has a very strong relationship with Macau because his advisor, Professor Liu Zhonglang, was from Macau. 也许大家不知道的是，姚教授其实和澳门很有渊源，他的导师刘炯郎教授就来自于澳门。So we are very proud that Macau, or somebody from Macau, actually already educate a scholar who win the Turing Prize or the Nobel Prize. 所以我们很骄傲地说，一个澳门人已经成功地教育了一个伟大的学者，使他得到了图灵奖或者等价的诺贝尔奖。As you all know, we have a very famous Qian Qiesun question. That means when Chinese can educate a Nobel Prize winner. 大家知道，这个钱老在去世之前问温总理，他有个非常著名的钱学森之问，说什么时候我们中国人才能教育出一个诺贝尔奖的获得者？我们今天很高兴地说，我们澳门人已经回答了钱学森之问，是完成时。So we're proud to say people from Macau already answered this question successfully. Nevertheless, Professor Yao actually not only as an accomplished scholar, he actually truly loved the country. He gave up his tenure and the chair professorship in Princeton and came back to China to start the computer science research in Tsinghua University. 不但姚启智教授在学术上这个造诣精深，更可贵的是他爱国之心。他放弃了在 Princeton 讲座教授的职位和终身教职，回到清华，带领他的团队 开拓我们计算机领域的新的研究。So without further ado, ladies and gentlemen, let's give a very hard applause to welcome Professor Yao to give the outstanding, fantastic speech.
Well, I'd like to thank President Zhao for a very kind and charming introduction. And Council Chair Xie, Rector Zhou, and President Zhao, and my dear colleagues and students and honored guests here. It's a great pleasure for me to come and visit Macau. This is actually the first time I've been in Macau, and for the last 2 days I have tasted many of the local delicacies and also the beautiful landscape and also the museums. It's certainly a wonderful place, and I'm so glad to have a chance to be here, and I will enjoy for the next few days. And the subject that I'd like to talk about today is quantum computing. And I think that most of you probably have heard about the concept of quantum computing. It actually is something that has led to great excitement in not only the computer science world, not only in the physics community, but actually in many of the popular press and magazines. After all, this really is the first serious revolution in terms of computing technology architecture. So compared with quantum computing, all the previous breakthroughs in computers, such as a new processor and the concept of clusters and so on, those were very conventional improvements. And the idea of making use of quantum physics to make computing faster is a concept that is truly different. And now, even though in general people find this concept very interesting, however, it's still some sort of mysterious to most people, even to computer scientists. What is quantum computing? And so today, I'd like to give a certain perspective on this subject. And we like to address the question, what is quantum computing at a more intuitive level, and why many find quantum computing so exciting. And specifically, I'm going to make my point by focusing on the following thing. I'm going to make the case that quantum computing is not only mysterious, it is not only very sexy, but actually it is a great science that is in the making. Now, it'd be very hard to define what great science is. And so I'm going to start by looking at some examples, some paradigms for great science. And then let's compare it with quantum computing. The first example I'd like to show is the X-ray crystallography. And many of us know that 100 years ago, Röntgen discovered X-ray accidentally. And it's a mysterious matter that is capable of making the film to lead to exposure. And now, exactly what this material is, was a great point of debate in those days. At that time, physicists knew of only two kinds of matters. One is the particles, and the other one is waves, like light wave and water wave. And now in 1912, von Loy confirmed that actually this new matter, this X-rays, they are waves, much like the light waves, by exhibiting a diffraction pattern of shining the X-rays through the atomic crystals. And so basically the idea is that X-ray actually is something that's like light wave, except that its wavelength is very small. So ordinarily, you will not be able to demonstrate its diffraction pattern until you have this great idea of shining it through a crystal whose dimension is approximately the wavelength of this X-ray. So you can see the wave patterns here. And now, those were great discoveries, and both of them won Nobel Prize. And actually, Roentgen won the first Nobel Prize in 1901 in physics. And now, the story continues. In 1913, Henry Bragg and Lawrence Bragg is a father-son team. They derived a mathematical formula to determine crystal structure from this. And they previously, people know that if you put X-rays through crystals, you can see diffraction patterns. And the Braggs had the great idea saying that if we can derive a math formula showing exactly what kind of pattern you would get from the crystals, then you can use it in reverse. By looking at diffraction pattern, you can figure out what the crystal structure is. And so this is a wonderful idea. And in 1920s, the structures of bigger molecules and metals and the organic molecules were determined using this method. And of course, when you get bigger and bigger structures, it becomes more and more difficult to use this method. However, but the progress continued. In 1937 to 54, Hodgkin actually were able to determine the structure of large biological molecules using it. And 1950s, Penrose and Kendall used it to determine the structure of the myoglobin, which is the molecule that's responsible for us to be able to breathe. And in the 50s, of course, the famous Crick and Watson and Wilkin and Franklin, the DNA structure based upon this method of crystallography. And now it continues even to today. It's the most promising, effective method for determining structures of molecules. So all the above achievements, about the 8 or 9 or 10 of them, all of them won Nobel Prizes for their discoveries. And so, no doubt, the X-ray crystallography is a paradigm for great science. And the second example I'd like to raise is computer science. And in 1901, Hilbert asked the question that whether it is possible to have some sort of way to mechanize the proof of theorems in mathematics. So I think no doubt this is the dream of every schoolboy, that from now on they are free from the tyranny of having to remember how to prove theorems. They just bring the computer and they can prove all the questions that teachers can throw at them. And now that has led to a series of development. The branch that interests us is in 1936, Alan Turing, by studying, thinking about that problem, invented the machine, the Turing machine model, which is the predecessor of the current computer. And of course, the Turing machine model invented by Turing was very slow if you implement it using the usual mechanical method. And in 1945, von Neumann designed a more practical design and others. They have made designs of computers using electronic components, and that began the widespread use of construction of practical computers. And of course, the transistors discovery started a revolution, which I think that by now the use of computers is everywhere, and the computer has enormous computing power compared to the old one. And this has enormous implications on the applications in all the sciences and engineering and the internet and the society everyday use. And so, no doubt, computers have changed our lives, and it's no doubt another paradigm of great science. And now, looking at these two paradigms, one lesson that we can draw from is that great science often happens when there's a disruptive technology which enables us to explore things which previously unimaginable. In the case of the X-ray crystallography, the invention of the X-rays and enables us to use this new tool to probe molecules and structures to make it possible to figure out how this material is constituted. And so that's the disruptive technology that enables us to do new explorations. And similarly, the electronic computer enables us to do computations that are wildly beyond our imagination before, and thus enables us to do things that, like electronic commerce, would be impossible 100 years ago. And I'm going to argue that quantum computing actually falls into following this particular pattern. And actually, I'm going to argue that quantum computing is a legitimate descendant of the two previous paradigms, namely the X-ray crystallography and also the computer software. So I'm going to explain it using an example. Now, the central idea of quantum computing is the following. So let's go back to the days when we didn't invent it. We haven't got the computers at hand. But we are just trying to figure out what kind of physical phenomena you can use that you can do computing with. And so from this regard, one can think about the X-ray crystallography as a kind of computer, namely that I have something I like to compute, namely the structure of certain molecule. And now, the tool that I have is a physical tool. I have X-rays. I can use the X-ray to get diffraction pattern, and which tells us something about the structure. And so I'm going to follow that approach. Suppose I have a certain function I would like to compute. So a function f for an input x. And let's try to do the computation not using an ordinary computer, but using a physical experiment in the following way. First, let me try to grow a crystal seed. And this crystal, the structure of this crystal, it's tailored for the particular function I would like to compute, and for the particular argument x that I would like to evaluate fx. And after I design the crystal, I'm going to shine an optical wave on this crystal. So it's kind of like X-ray. It's a variation. And now if I design the wave and I've designed the crystal properly, I might be able to see some diffraction pattern. And by looking at diffraction pattern, perhaps if I'm lucky, I may be able to figure out what's the value of f of x. Okay. So let me so that's the first part, namely to make use of the paradigm for X-ray crystallography. And now the second part is that if I, as we are going to see in a few minutes, if I just grow this crystal in a straightforward way, it's going to be exponentially large. So it will be too large for me to be useful to do the computation. However, it is sometimes possible that if you use a software simulation of the process, you don't need to build the whole device. You can just simulate the running of this experiment. And actually, if you are lucky, you might be able to exponentially cut down the size so that it will be possible to actually using quantum physics to finish the job of figuring out what f of x is. Okay, so this is a high-level view of what I'm going to say. And now let me show you a specific example on how this can be done. And I'm going to use it from a paper by Simon in 1994. And so he proposed a problem, and he proposed a quantum algorithm for solving it in the following way. That the problem is the following. And just imagine that in the local shopping center or the department store, they sell the Christmas gifts for ambitious kids. So you pick up one, and you want to take it for your children or friend. And now, this toy is a black box. And it's capable of taking in an input, an n-bit string, and then it's going to give you an output string, f of x. And now, this transformation f is a 2-to-1 mapping, in the sense that there are 2 to the n possible inputs. There are 2 to the n different input strings. The output strings, there are only half of as many. And actually, every possible output, you can get it from 2 input. And furthermore, they are related by a mapping, namely that this box has a secret binary string, an n-bit string, so that the 2 inputs which led to the same output is related by a translation of the amount of s. So it's one argument is x, and the other one is x plus s. And so the question is, if you have such a black box, and you were told that there exists a secret s for this black box, the question is, can you find out what this secret is? So there's a secret associated with this black box, and you would like to figure out what this secret is. And it's possible to show that there's no way you can figure out what this is, what this s is, unless you do exponential amount of trials. Because in principle, if you try all the possible input streams, of course, at some point, you are going to find a collision. You will find 2 inputs that gets you to the same output, and therefore you can just figure out what this s is by comparing these 2 inputs. However, if you don't use an exponential number of inputs, if you just try a few number of inputs, a polynomial number of inputs, you will have no chance of having this collision. And therefore, for all practical purpose, the black box is just a total random black box, and you don't get any information about it. So therefore, this is probably something which cannot be done in the classical world if you use only the classical logic and machineries. Now, however, if you have a quantum lab, then you have a chance of doing it, as we'll show you how. And just recall, in elementary physics, the phenomenon of diffraction, you have a light wave of a single wavelength. And if you let the wave propagate through a first screen, so the first screen is drilled with holes on it. And now you put a second screen behind the first screen, then the light source going different holes on the first screen, they would going from here, they would interfere, and you're going to see a typical diffraction pattern. So it's somewhere is bright and somewhere is dark. So it's now exactly how the pattern looks like, and in particular what the spacing between different dark spots depends on a function of the physical setup, the wavelength and the various distances and so on. It tells you something about the setup. And now, from this perspective, the X-ray crystallography is just to replace the first screen with a crystal. So the X-ray coming from here would get propagate to the different things, and they would show a diffraction pattern because of the structure of the different crystals. So the X-ray crystallography is exactly by looking at how the pattern goes to figure out what the crystal structure is. And now what we like to do is something that's very similar. We like to grow a crystal. And now, the crystal, this is a Gedanken experiment. It's a thought experiment. You grow a n-dimensional cube. Okay, so you have a cube with 2 to the n, a crystal with 2 to the m vertices on it. And so that, let's imagine you have a certain light that goes through it, and the light would go through each of these vertex and then propagate to the second screen. And we want to design it in such a way that it can get us a good diffraction pattern for our purpose. And specifically, the X, the light coming from here, is going to propagate to the second screen exactly on a horizontal line. So this is a two-dimensional kind of screen with 2 to the n by 2 to the n lattice points on the screen here. And the light from here is going to all propagate to this horizontal line, and the height, this coordinate here, is determined by the black box. So that's how the black box is incorporated in this experiment. Okay, so we design a way such that it makes use of the black box to get us a experiment. And now you can see that if you consider the pair of vertices which are the conjugate to each other, one is x, the other is x plus s, they have the same f of x. So therefore, the amplitude would interact from these two vertices. And now if you look at the amplitudes, the magnitude are all the same. The sign could be plus or minus depending on x, the inner product of x and y. Then what happens is that the light coming from these two places, they would sometimes they would reinforce each other so that the amplitude is doubled, and sometimes they would cancel out exactly. Okay, and now and if you open up to look at all the vertices, then it's going to generate points. And now, each bright spot, y, is going to tell you the story that the secret S must satisfy the equation that S dot y modulo 2 equals 0. So this actually is the inner product of two n-bit vectors, so therefore it's a linear equation in the secret S. So there are n bits in this S, and each bright spot is going to give you a linear equation telling you something about one bit of information about the secret S. So therefore, this secret is computable from the location. If you only have n bright spots, is enough. I mean, there are exponential number of spots, so of course you'll be able to figure out what this S is. Now, the drawback of this physics experiment is that it's an exponentially large experiment. The number of holes is equal to the size of the crystal is 2 to the n, and the number of points on the second screen is also 2 to the 4n. So therefore, you cannot actually use any physical way to construct it. Now, here is the part that we combine it with the computer magic. So instead of constructing the hardware for this quantum experiment, what we can do is that we can just simulate what's the propagation of one photon coming from the source through this imagined crystal, and to see where the photon would land on the second screen. And each simulation, if I can simulate this in a logarithmically amount of steps, then it will give me 1 bit of information on the secret. And so quantum computer is such that makes it possible to simulate the hardware experiment, the optical experiment I just described, using a polynomial number of bits in order to do it. So there's no need for all the vertices. You only need a linear number of quantum bits. And so if you have quantum computer, you can implement the above experiment with only 3n quantum bits. And so you can simulate this one quantum to one spot at one at a time with just a polynomial amount of work. And so you're a very bright kid in the quantum lab basement can figure out, using this quantum computer, can solve this classical impossible problem just with a polynomial number of steps. Okay. Now, Simon's result is not, it looks like a toy theorem, but actually it has important inspiration for future work. Actually, Peter Shor's very famous quantum algorithm for factoring large numbers, actually it's quite similar in spirit to the Simon's algorithm that I just described. It's kind of the group of the n-dimensional cube is replaced by the modulo n on the group on the line. So in Peter Shor's case, he has a secret, which is you have a large integer, which is the product of two prime numbers, and so this prime number can be regarded as a secret. So that we would like to determine, and Shor's method is to do it in a framework that we have just described. And now, to recapitulate, the great science often happens when the scientific theories interact and scientific disciplines interact and new technology becomes available. And now, quantum computing is in this happy situation, and it's firstly the quantum theory and the computer theory would interact. And the new technology, the ability for us to manipulate small object, quantum object, has become possible in the last 30 years, and that's why quantum computing now, the theory can actually be put into practice. And in the last 20 years, since the quantum computing has become popular in the popular press and also in scientific research, many people have always thought that this really is a pie in the sky, and we will not, in our lifetime, see a real quantum computing. But actually, I think that quantum computers is something that will come sooner than what most people expect. And one indication is that if you look at the many of the scientifically advanced countries in the world, they all put money, lots of money, into building centers for quantum information and building quantum computers. And just to show some example, and all this really happens in the last 10 years, when the indication became, at least to the insiders, much more hopeful than people realize. And for example, in the US, at the National Institute for Science and Technology and University of Maryland, they have a joint large quantum institute funded by by the funding agencies in the U.S. With 29 professors, including Nobel laureate Phillips, and Harvard MIT have a large center for ultra cold atoms, and including the Nobel Prize laureate Ketterle. And now at Caltech, and here's that you might surprise you, the Microsoft research. They have something called a Q Station at Caltech, and they have with 17 professors, including Fields medalist Michael Friedman, and supported by the government agencies and Microsoft. And in Canada, the Perimeter Institute and University of Waterloo, they have a very large institute for quantum computing, and started with $100 million US. In Singapore, at National University of Singapore, they have constructed a center for quantum technology with a lot of the startup fund, and there are centers in Max Planck in Germany and Japan, and even in China. And now, one indication that I'm very hopeful that the quantum computer will come sooner than you think is that at Tsinghua we have made a commitment to work in this area, trying to build a quantum computer. And now there's I'd like to introduce a little bit a quantum network project in our institute at Tsinghua University. And now, well, firstly, just think about that internet nowadays. It's so vital for the society. And now, the question was first raised by Jeff Kimball at Caltech, that is it possible to construct a quantum internet? Is it possible? Now, the current internet is that everyone on the net, at the minimum, you can send classical messages from one place to another very reliably. Now, the question, the analogous problem in a quantum internet is that, is it possible to construct a quantum network so that any person on the net can send a quantum signal over this quantum internet faithfully to any other point in the internet? So you actually, so that's the basic thing that you can do, but of course you can do a lot more, as in the classical internet case. And now, why are we interested in building quantum internet? And one reason is that a quantum network is needed for the practical realization of building a scalable quantum computer. And so there are a lot of, in building a quantum network and a quantum computer, you have to go through building a classical network, classical internet, starting from the very basics, building the memory and building the interface, and so on and so forth. Every step is a big scientific endeavor. So it's something that is a research project. And now, the quantum network is needed for building a scalable quantum computer. And now, let's look at the technology for building quantum computer, quantum network. And one person which is very much responsible for making this technology nowadays becoming very promising is David Wineland. And I think that many of you probably know that David Wineland just won the Nobel Prize in October for his work of this technology, that using the ion trap technology to build quantum memory and quantum processors. And by using the idea that he has, subsequently, people, through the research of many people, it turns out that from this very humble beginning of just something that can store a few bits of quantum qubits, it's possible to design a scalable quantum computer. And the basic idea is really very similar to the classical supercomputers. Nowadays, one approach of building scalable supercomputer is that you just take some small computers and you connect them by networks and using the appropriate protocol to make it possible to do work collectively, to become bigger, as big as you want, the supercomputer. And now, in the quantum case, it's also, you can use this paradigm. You start out by building very small quantum memory, and you connect all this together in a quantum network, and then eventually you can get a, if you do it properly and with a lot of theory, then you'll be able to build large-scale quantum computers. And so this is kind of you can have quantum registers, and you connect them together, and you'll be able to make them interact and do computation. And the idea that Wang had of using quantum, of using ion trap technology is that so this is what schematically you will have a tube containing a linear array of ions, and you'll kind of keep them in place by electromagnetic fields, and then you make it to be the vacuum very pure and also very cold temperature, and you'll be able to manipulate things with lasers to make them interact and do computation. And so one good sign that people are making progress is that if you look at some of the leading journals in science, like Nature or Science, every few issues there will be some progress of something about how many more bits you can do, and what kind of interface you can do. And all these are very, I'm not going to get into the detail of this. It's just that I just want to illustrate that for example, if you want to have the storage interact with the photons, you will have to do a lot of work using a lot of physics in order to do it. Okay. And so let me come to the conclusion. I hope that I've convinced you that firstly, the great science often happens when the scientific theories interact and scientific disciplines interact and new technology becomes available, and quantum computing is happening at this right time. And secondly, I want to come back and be honest with you because in the very beginning I say that it's a very hard thing to argue about something is a great science. If you start out, instead of looking at what great science is, I just try to convince you by analogy. And now I want to come back to the question of what is great science, and to look at this question straight on. And of course, everyone would have a different opinion on questions of this kind. And but I think that we all can agree at a very basic level, it must have two merits. Firstly, it must have deep impact. And now, quantum computers actually will have great impact. Not only that it's the natural extension of the current information technology, but it actually, if we have quantum computers, we can solve a lot of things that we previously cannot do. For example, one of the hottest topics right now in the quantum information processing is quantum simulation. It can help to solve quantum equations. Right now, there are many quantum theories, such as the high temperature superconducting theories, that people have different theories and different equations, but nobody can deduce what the consequences of these equations are, because we simply do not know how to solve these equations with classical computers, because it takes exponential amount of work to solve a quantum equation. But if we have quantum computers, we can solve these quantum equations numerically, and we will be able to deduce, this theory is right, the other theory is not right, and therefore we can lead to progress and may help us in other things like designing new materials and so on. And the second one is that looking at the even higher level, I think that's something that merits to be a great sign. It must be that it's not just to promote the increasing of our material comfort. It must in some way uplift the human spirit so that we can all feel better about the world and about ourselves and getting intellectual delight out of it. And now in this regard, let's think about the fantasy that we all had in our youth, in our childhood, that we imagine to be great adventures to the jungles, to the mysterious places, perhaps to a small unexplored little island, say in the South Pacific somewhere, where perhaps there are a group of people living there who have never been touched by modern civilization, and they speak a language that we kind of understand the grammar and so on, but never had a chance of actually coming into contact with them. And I think that the ability of quantum technology is like that. Physicists have taught us the language of the macro world. So we have all these little electrons and particles which are part of us, but they speak a very different language. And we have somehow understood their language for over 100 years. But now, suddenly, the modern technology in the last 30 years have made it possible for us to actually visit those little islands, and we'll have a chance to have a conversation with them. And just imagine our quantum factoring algorithm, and we can use the program of the quantum factoring algorithm, we can tell these little inhabitants, these little particles about it, and we will say that would you be so nice as to dance, to choreograph yourself according to this script and do the dance for us. And they would do it, and they would leave some prints, some numbers on the sand of the little island, and those numbers would just be the prime factors of the large integers we want to factor. And I think that, isn't there anything more uplifting than this scientific story? Thank you very much.
多謝姚教授嘅演講啊！請教授留步，接落嚟有請澳門大學趙偉校長到台上為我哋主持問答環節。Thank you, Professor Yao, for your lecture. Now we come to the Q&A session. May we invite Reta Wei Zhao of the University of Macau to be the moderator of this session.
Thank you, Professor Yao, for such a great lecture. Now we open for questions and answers. Yes, Louis.
Thank you very much, Professor Yao, for this very interesting presentation. Being a hardware guy, so we work in microelectronics, we have a steady lab in microelectronics here. After seeing your presentation, this means with this technology in future, you don't need transistors anymore. That's true?
I don't think that the quantum information processing is going to catch up with the electronic devices that we have right now in the conventional tasks. I think that so the transistors, I think that will still be the preferred choice for the standard tasks. Now, however, quantum technology will have two things. Firstly, it will enable you to do things that which previously you cannot do, and secondly, and that's an intriguing possibility, namely that the future transistor we may really have to make use of quantum devices in order to do it. I think that that it's certainly, I think that you are an expert, so you know that Moore's law probably will not be able to go on for the next 20 years. So at some point, we hit the quantum limit, and so we have to design things that taking the quantum effect into account. So I think that your question, will we see a very different transistors? I think we will, and will be something that use some sort of molecular switching and so on. And so I think that from that point of view, I think that the answer to your question is right, that we'll have to see some very different devices in the future.
Okay. Thank you very much. I think I will still have a job for a few years. Thank you very much.
Thank you. Professor Yao, actually in the audience, we actually see many young faces here. They actually from high school, they come over here. I believe maybe many of them will be Professor Liu Junlang 20, 30 years later, educate more Turing Prize, Nobel Prize winners. But given the context in Macau, I talk to the high school kids from time to time. We always have a question. That is, should we learn science in Macau? Macau is a small place. We have a lot of money. We make money very quickly through casinos. So nobody here is going to learn science to make money. So in that context, should the high school kids learn science, mathematics, physics? You keep mentioning your lecture. If they learn, for what purposes?
I think they should learn. I think that, firstly, the reason that you want to learn sciences is because science actually provides an extra dimension to one's life. Knowing some mathematics, knowing some physics, actually makes it possible for you to appreciate some aspect of our worldly existence that you otherwise wouldn't be. So let me use an analogy. I think we all know that musicians and painters and artists, especially the good ones, when you see them, you know that they can get pleasure. I mean, I think that if I hear Beethoven the Fifth Symphony, I get some excitement. But I know that when musicians hear that, I think they would kind of go up and down, and I can see that they go into a different world. And it's the same thing with the paintings. I think I have to admit that when I go to the museum, I think even at the masters, the Van Gogh and the Matisse, I think that I can stand there for 1 minute and I can say that, well, I think this is really great. I'm truly happy. But I think it is definitely, I know that if you are some great appreciation of art, you will get something a lot more about it. And actually I have personal experience with it, and that makes me so convinced of this is true. I once was in the hospital and I was in a high temperature, and I just kind of I think to the outside world I was very unconscious, but I was dreaming, and in the dream I was a great painter, and I saw all the colors so distinctly, and at that time I told myself, I said that I really understood why some people can paint, because I knew, I was very confident in the dream that that I know exactly all these patterns and I can draw them as good as any genius. And when I woke up, I forgot, I couldn't, I knew I was excited, but I couldn't recapture the excitement that I had at that time. But it did convince me of one thing, namely that I know that there are things that people with different talents, they can appreciate it. So therefore, now coming back to the point, that we all encourage the young kids, the high school, to have some accomplishments in playing piano or reading poetry and so on. And one reason is that this makes them to be a better person. They can appreciate the finer things of life. And I think that the math and science, they have the same purpose. I think that that if you understand something about the spirit of science and physics, it will go with you to make you a better person in your life. And also, I think that it will enable you to compete in the modern world. So I think that they should. And let me also tell you that I know that the University of Macau, especially under Professor Zhao, is really going to make University of Macau a really outstanding, first-rate university, and I think that's going to do a lot for Macau. And let me say this from my experience at Tsinghua University. And well, you know that even though Tsinghua University is a very good university in China, and but all our undergraduate students, when they graduate they want to go to the United States. I think for many years they want to go out but we started a quantum computer program just 2 years ago, and then suddenly we were able to keep a lot of the students, especially the physics students. They already were determined to go to the U.S., but they stayed to become graduate students in our institute. And the reason is because they were excited that we are going to the forefront in science. We are building quantum computers for China, and they think it's very exciting. So as University of Macau, under the Professor Zhao's leadership, is going to expand and to become a truly great university. And I think that many of the local students and even students from Hong Kong and other places, they would want to come to University of Macau in order to learn things that would actually elevate their life. Because I really don't think that anyone should plan their future, to make their future plan based upon how much money they can make. Because I think that in the future society, it's very easy to make a comfortable life with all the gadgets, all the mobile phones, and so on. I think that's not a problem. The problem is that how can you have a life that can intellectually to make you see more things and therefore live a richer life. And I think that's why it's very important to build a great university.
Thank you. So please remember, we should plan our future by making greater science, not making greater money. Any other questions? Yes.
Thank you, Professor Yao. Gave us a very wonderful talk. And I'm Alfred Brock from Faculty of Science and Technology. I have interest about that because you are quite successful. I think that time management is quite important in the successful path. So can you share your experience to us in time management so that our students and college know how to well handle our time? So thank you.
Graduate students don't have enough time. That's the issue.
Well, firstly, let me have a disclaimer. And I think my wife thinks I'm a very lousy time management person. So I mean, with that caveat, well, let me say that I think people go through different stages, and at a different stage, that there are different priorities. But I think that one advice I can offer is that for people who have seriously become interested in pursuing a scientific career, and I think that for people who have decided to do that, I have one great time management trick, namely that you spend 100% on learning and thinking about science. And I just remember reading that there's a famous quotation from Professor Chen Xingsheng. I think Chen Xingsheng says that well, maybe I'll say it in Chinese, which is more suitable. That 我每天早上起来7、8点钟我就开始想的就是数学，一直到我晚上睡觉为止。我数十年如一日，到现在还是如此。So I think that in order to try to be a really great scientist, aside from having talent, you really should be so interested that you would divide 100% time to it. So in that sense, time management is very easy.
Thank you. We have time for the last question. Please.
Thank you. So in your opinion, what's the impact of quantum computing to the traditional cryptography? Because it seems that with the quantum computers, we can solve the previous very difficult problems. For example, factorizing big numbers, using polynomial time. So is it a threat to the traditional cryptography? Thank you.
Yeah. If quantum computer becomes a reality, then many of the most secure encryption methods would become obsolete. And actually, the NSA, which is the U.S. intelligence agency, was the first agency that began interested in sponsoring quantum algorithms research. And precisely because that it can break, it can factor large numbers, and thereby it can break the RSA algorithm, and actually can break other systems like based on the elliptic curve and discrete logarithm algorithm. So many of the algorithms which right now are thought to be super secure will be broken. So I think that's a very pragmatic thing. And let me just say that the beauty of scientific research is that you never know where it's going to end. The one question, one result leads to another question. For example, the fact that the quantum computers can break secure encryption method actually have made people very interested in developing quantum encrypting method. So the quantum encrypting method will be so secure that if you have quantum computers, you will still not be able to defeat it. So I think that's also something that we should keep in mind, that the development of the quantum technology is not just the things that we can see right now, but it's the things that we have not yet seen. So.
Thank you. Thank you very much.